For nearly a century, black holes have been considered the most extreme objects the universe can create. They trap light, they crush dying stars, they mark the point where gravity appears to overwhelm every other force in nature. But there is a problem. At the center of every black hole, Einstein's equations predict something physics cannot accept: a singularity, a place where matter is compressed into zero volume, density becomes infinite, and the mathematics itself stops making sense. What if that never actually happens? In 2001, two theoretical physicists proposed an extraordinary alternative. The same equations that predict black holes also allow for another object, one that could occupy the exact same place in space, produce the same gravitational pull, cast the same shadow, and remain indistinguishable from a black hole to every telescope humanity has ever built. It is called a gravastar. If gravastars exist, then singularities may not exist at all. Instead of hiding an infinitely dense point, they may contain a bubble of dark energy, the mysterious force driving the expansion of the universe itself. Unlike black holes, gravastars would have a real physical surface, a boundary made from one of the most exotic quantum states ever proposed by physics. Anything falling onto that surface would not simply vanish, it would collide with something. Even more unsettling, every image of a black hole, every gravitational wave signal, and every observation collected so far is still consistent with the possibility that we have been looking at gravastars all along. For more than 2 decades, physicists have searched for a decisive way to tell the difference. They still cannot. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. Now, let's begin. Before we can understand why anyone imagined a gravastar, we have to linger at the deepest fracture inside the familiar picture of a black hole. Everything depends on one unsettling destination. At the center of the classical description lies the singularity, a point where every piece of matter that created the black hole has been compressed into zero volume. Density climbs beyond every imaginable limit until the mathematics no longer returns an enormous value. It returns infinity. That single result changes everything. Infinity sounds dramatic, yet within physics, it usually signals something much less triumphant. It tells us the theory has wandered beyond its own ability to describe reality. Imagine looking at a speedometer that suddenly reads infinity. You would not conclude the car has reached an impossible speed. You would conclude the instrument has failed. The singularity raises the same concern. The equations stop describing nature with confidence and begin exposing the limits of the model itself. This difficulty emerges from general relativity, Albert Einstein's remarkable description of gravity, still regarded as the most successful large scale theory ever created. Again and again, its predictions have matched observations across the cosmos with astonishing precision. Yet when those same equations are followed all the way into the heart of a black hole, they arrive at a destination where space, time, and matter lose every ordinary meaning. The mathematics continues. Our physical understanding does not. The story reaches back to the year 1916, during the First World War. From military service at the front, Carl Schwarzschild discovered the first exact solution to Einstein's newly published equations. He sent his calculations to Einstein through the mail, revealing a strange possibility hidden within the theory itself. Only 6 months later, illness contracted during the war claimed his life. He never witnessed the extraordinary legacy of those pages, nor could he have imagined that generations of physicists would spend more than a century debating their deepest implication. For roughly 85 years, the singularity remained an accepted destination, or at least a problem postponed for future minds. Many researchers viewed it as a marker showing where a more complete theory would eventually take over. It became a placeholder for missing knowledge, patiently waiting while observations, experiments, and mathematics advanced together. But waiting also carried a cost. The contradiction never disappeared. Then a different possibility emerged. Pavel Mazur and Emil Matola looked toward the final stages of collapse and hesitated before accepting the traditional ending. They wondered whether matter truly continued without interruption into mathematical impossibility. Could nature change course before reaching that final point? Their search began with the singularity itself, yet it gradually transformed into something far more unexpected, a proposal that replaced the familiar ending with an entirely different cosmic object. A massive star reaches its final heartbeat almost without warning. For millions of years, it has balanced gravity with the tremendous pressure produced by nuclear fusion deep within its core. Then the fuel is exhausted. The outward support fades in less than a second. What had remained stable for ages suddenly begins falling inward under its own overwhelming weight. The collapse accelerates with astonishing speed. As you follow the shrinking core, gravity tightens its grip with every passing instant. Material races inward at a substantial fraction of the speed of light. In roughly the time it takes to blink, a core once comparable to the size of Earth contracts until it occupies a region closer to the size of a city. Every layer presses upon the next. Every moment increases the pressure. Within the traditional picture, nothing interrupts this descent. Gravity continues strengthening as matter is squeezed beyond the densities found inside neutron stars, which are the crushed remnants of massive stars composed almost entirely of tightly packed neutrons. Compression continues beyond every state of matter that laboratories or observations have ever revealed. The equations simply carry the collapse onward toward the mathematical destination we have already encountered. But Pavel Mazur and Emil Matola wondered whether nature truly follows that uninterrupted path. They proposed that there exists a precise threshold where the familiar rules governing collapsing matter give way to something profoundly different. At extraordinary density and extreme temperature, quantum mechanics, the theory describing nature at the smallest scales, could transform the collapsing material itself instead of allowing it to continue unchanged. We already know that matter can reorganize into entirely new forms. Water provides a familiar example. As its temperature reaches the freezing point, individual molecules rearrange into the ordered structure we recognize as ice. The substance remains the same at its most basic level, yet its behavior changes completely because its internal organization has shifted into a different phase. The proposed Gravastar transition follows the same fundamental idea, though on a scale unlike anything else in the universe. Matter subjected to immense gravitational compression reaches a critical condition where its quantum properties reorganize into an exotic state that resists any further squeezing. Gravity still presses inward with extraordinary strength. Yet the material itself has become something fundamentally different from the matter that began the collapse. Everything changes there. The inward plunge comes to an end. No familiar force rises to oppose gravity. Instead, the transformed quantum state no longer permits additional compression. The collapse simply cannot proceed in the way the classical equations once suggested. What remains afterward carries the same enormous mass and nearly the same outward appearance expected of a black hole. Yet its interior history has taken a completely different path. You are no longer approaching a singularity. You are approaching a gravastar, An object whose hidden structure may prove even more astonishing than the cosmic abyss it was once expected to become. Imagine peeling away the layers of a gravastar one by one. Each boundary carries us farther from ordinary physics and deeper into conditions that no natural experience can prepare us for. What appears from afar to resemble a familiar compact object gradually reveals an internal design unlike anything else proposed in modern astrophysics. We first encounter an incredibly thin outer shell. This shell is composed of matter compressed into a Bose-Einstein condensate, a quantum state in which individual particles surrender their separate identities and behave as one unified quantum object instead of countless independent pieces. Rather than acting like grains of sand gathered together, the entire shell responds as though it were a single entity sharing one collective state. This remarkable form of matter is not merely theoretical. In the year 1995, Eric Cornell and Carl Wieman first created a Bose-Einstein condensate in a laboratory at the University of Colorado. Their achievement demonstrated that quantum behavior could emerge on scales large enough to observe directly. It transformed a long-standing prediction into measurable reality. That accomplishment later earned them the Nobel Prize in Physics in the year 2001. The very same year, Pavel Mazur and Emil Motola introduced the gravastar concept. Creating such a condensate on Earth requires extraordinary conditions. Scientists cool atoms to within roughly 1 billionth of a degree above absolute zero, among the coldest temperatures humanity has ever produced. But inside a gravastar, the destination is reached through an entirely different route. Immense gravitational compression reorganizes matter into the same quantum state without relying on extreme cold. The ending is familiar. The journey is completely different. This shell forms a genuine boundary. It is neither ordinary matter nor an invisible mathematical surface. Every part of it exists as a vast quantum structure wrapped around the object, like an extraordinarily thin sphere standing against one of the strongest gravitational environments known. Passing beyond that shell brings us somewhere even stranger. The interior contains no atoms, no familiar particles, and no conventional substance. Instead, theoretical models describe a region filled with dark energy, the mysterious component believed to drive the accelerating expansion of the universe itself. Here, that expansive influence is confined inside the surrounding quantum shell rather than spread across the cosmos. But equilibrium emerges from this extraordinary arrangement. The concentrated dark energy presses outward, while gravity and the condensate shell press inward. Neither side gains complete dominance. The opposing influences balance one another with astonishing precision, allowing the entire structure to remain stable instead of collapsing further. The deepest surprise awaits where we expect a center. There is none. The singularity has disappeared from the picture entirely. Spacetime within the interior follows a different solution of general relativity, one where repulsive behavior replaces endless collapse. We find ourselves contemplating an object that outwardly resembles a black hole while concealing something far more extraordinary, a miniature region of cosmic expansion enclosed within a quantum shell, carrying the appearance of one universe while sheltering another inside. Every journey toward a compact object eventually arrives at one defining boundary. From far away, you would notice almost no difference between the two possibilities we have explored. Gravity guides surrounding stars in the same way. Light bends along nearly identical paths. Yet everything changes at the final destination, where one object offers nothing to touch while the other presents a genuine physical surface. A classical black hole possesses an event horizon, the boundary beyond which nothing returns. Despite its importance, this boundary is not made of matter. It has no physical material, no texture, and no structure waiting for an incoming traveler. According to general relativity, someone falling inward would experience no special sensation while crossing it. The event horizon marks a change in the geometry of spacetime itself, rather than the beginning of a physical object. But a gravastar tells a very different story. Its outer shell forms a real surface composed of the remarkable quantum state we encountered earlier. This surface exists as actual matter. It can interact, it can respond, it can exchange energy with anything that reaches it. Instead of continuing inward without interruption, incoming material encounters a genuine boundary. That encounter is extraordinarily violent. Gas spiraling toward the gravastar eventually strikes the condensate shell at an enormous fraction of the speed of light. The tremendous kinetic energy carried by the falling matter cannot simply disappear. It is converted into intense radiation, heat, visible light, and ripples in spacetime known as gravitational waves, which are traveling distortions in the fabric of space and time created by accelerating masses. The surface becomes unimaginably energetic during periods of active feeding. Theoretical models indicate temperatures many orders of magnitude hotter than the Sun's interior, where temperatures already reach roughly 15 million degrees Celsius, or about 27 million degrees Fahrenheit. Instead of swallowing everything forever, the shell transforms incoming energy into new outward signals that continue their journey across the universe. This distinction reaches beyond heat and light. It reaches into one of modern physics' deepest puzzles. Information, the complete physical description of matter and energy, is expected by quantum mechanics to remain preserved throughout every process. A gravastar naturally respects that expectation. Material striking the shell interacts with it, changes form, and is eventually re-emitted in different ways. The original information is transformed rather than erased. A black hole presents a far more difficult picture. Once matter passes beyond the event horizon, every observable trace appears permanently inaccessible. This apparent disappearance gave rise to the famous information paradox, a conflict between the predictions of quantum mechanics and classical black hole theory that has challenged physicists for decades. But the gravastar avoids that conflict through its very architecture. Without an event horizon, there is no permanent hiding place for information. The paradox loses the feature that created it in the first place. What first seemed like the strangest part of the gravastar ultimately becomes its most coherent one, preserving the consistency that physics strives to maintain. Sometimes the importance of an idea is measured by the number of problems it touches. Gravastars entered physics as an unusual proposal, yet their influence reaches far beyond one alternative description of collapsed stars. They stand at the intersection of three of the deepest unresolved difficulties in modern theoretical physics, each one rooted in the same classical picture of a black hole. The first crisis begins at the very center. General relativity, the theory that has described gravity with extraordinary success for more than a century, predicts that matter is compressed into infinite density. That result has troubled physicists since the earliest studies of black holes. Infinity inside an equation signals that the mathematical description has reached a limit where it no longer explains nature with confidence. For well over 100 years, no widely accepted replacement has emerged, but the gravastar model removes the singularity completely. Without that infinitely compressed point, the breakdown disappears from the theory. The second crisis reaches even deeper into the foundations of physics. Quantum mechanics, the framework governing the smallest known scales of reality, has survived experimental testing with astonishing precision. Some measurements agree with its predictions to within roughly one part in 1 trillion. One of its central principles is that information cannot simply vanish from the universe. Every physical process preserves the complete description of what entered it, even if that information becomes extraordinarily difficult to recover. Classical black holes seem to violate that rule. Matter crossing the event horizon appears lost forever from the observable universe. The contradiction between quantum mechanics and general relativity became known as the information paradox, and it has inspired decades of debate among many of the world's leading physicists. But a gravastar offers a different outcome. Material interacts with its physical surface, changes form, and returns energy outward. Information remains part of the universe's ongoing story, instead of disappearing beyond an unreachable boundary. The third crisis arrived much later. In the year 2012, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully proposed what became known as the firewall paradox. Their argument followed an unsettling chain of logic. If information ultimately escapes through Hawking radiation, the theoretical radiation predicted to emerge from black holes through quantum effects, then the event horizon cannot remain the smooth crossing predicted by general relativity. Instead, it would become a barrier of extraordinary energy, capable of destroying anything attempting to pass through it. Such a conclusion directly conflicts with one of Einstein's central principles, the equivalence principle, which states that free fall, through gravity, should feel locally indistinguishable from ordinary motion. But the gravastar never creates that conflict. Without an event horizon, there is no place where a firewall could arise. The contradiction simply has no structure on which to exist. One proposed object therefore reshapes three separate crises at once, leaving behind a picture where the mathematical tensions that have challenged physics for generations lose the very conditions that allowed them to emerge. The deepest chamber of a gravastar cannot be understood until we pause beside one of the greatest discoveries in modern astronomy. Everything within this hidden interior depends on a mysterious ingredient that fills almost the entire universe, yet remains almost completely unexplained. We call it dark energy, a name that describes its effects far better than its true nature. For much of the 20th century, astronomers expected the expansion of the universe to be slowing. Gravity, after all, pulls matter together. It seemed reasonable that billions of galaxies should gradually lose speed as they drifted apart. But in the year 1998, two independent research teams measured the brightness of distant exploding stars and reached the same astonishing conclusion. Expansion was not easing with time. It was accelerating. The universe grows larger every passing moment. Even more remarkably, that expansion proceeds faster today than it did yesterday, and faster yesterday than it did 1 million years ago. Something is steadily stretching space itself across unimaginable distances. Every observation points toward the same invisible influence. That influence is dark energy. It has never been seen directly. No instrument has captured it as a particle or identified its physical composition. It carries no known mass in the ordinary sense, and it interacts so weakly with familiar matter that gravity remains the only clear sign of its presence. Yet its effect differs from ordinary gravity. Instead of drawing regions together, it encourages space to expand. Current observations indicate that dark energy accounts for roughly 68% of the total energy content of the universe. Ordinary matter, including every planet, star, galaxy, and living creature, contributes only a small fraction by comparison. The dominant ingredient of the cosmos remains almost entirely unknown. But the mathematics leading toward this strange picture began much earlier. In the year 1917, Albert Einstein introduced a mathematical term called the cosmological constant into general relativity while attempting to describe a universe that neither expanded nor contracted. After astronomers later discovered that the universe truly was expanding, Einstein abandoned the idea and reportedly described it as his greatest blunder. Then the discoveries of 1998 brought that same mathematical concept back into serious discussion because it naturally produces accelerating expansion. Within the Gravastar model, this expansive influence does not remain spread thinly across intergalactic space. Instead, it fills the object's interior as a concentrated region where dark energy dominates locally. General relativity allows such solutions through what physicists call negative pressure, meaning a form of energy that drives expansion instead of contraction. This is a mathematical property of space-time itself rather than an ordinary pushing force. But the implications become extraordinary. A gravastar could contain one of the most concentrated reservoirs of dark energy anywhere in the observable universe, sealed inside an object far smaller than a typical planetary system. If gravastars truly exist, dark energy becomes more than a distant property of the cosmos. It becomes something local, physical, and capable of gathering into one remarkable place, reshaping our understanding of the universe's most mysterious ingredient. Some discoveries arrive as light crossing immense distances, others arrive as motion itself. In the month of September, during the year 2015, scientists recorded something entirely different. Deep beneath the surface in the state of Louisiana, the Laser Interferometer Gravitational Wave Observatory detected a ripple in spacetime that endured for only about 0.2 of a second. That fleeting signal transformed astronomy forever. The source lay about 1.3 billion light years away. Two black holes, one weighing about 36 times the mass of our Sun and the other about 29 times the Sun's mass, had completed their final spiral and merged into a single object. During that brief instant, they released more energy than all the stars in the observable universe produce over the course of an entire year. Yet by the time the disturbance reached Earth, its effect was astonishingly small. The stretching and squeezing of space-time measured by the observatory amounted to less than 1/10,000th of the diameter of a proton. Even so, the instrument detected it. That achievement opened the era of gravitational wave astronomy and earned the Nobel Prize in Physics in the year 2017. Humanity had gained an entirely new way of exploring the universe, listening through vibrations instead of looking through light. Every merger produces its own recognizable pattern. The signal begins with a steadily rising chirp as the two compact objects orbit faster and closer together. It reaches a sharp peak when they finally unite. Afterward comes the ringdown, the period during which the newly formed object settles into equilibrium, much like a bell gradually losing its vibration after being struck. For black holes, this final stage follows an exact mathematical pattern known as quasi-normal modes, meaning the characteristic vibrations expected from a disturbed black hole. Observations collected so far match those predictions with remarkable precision. But gravastar models introduce a fascinating alternative. Instead of absorbing every gravitational wave entering the interior, the concentrated dark energy is predicted to reflect part of that disturbance back toward the surrounding shell. Those reflections would create additional pulses after the primary signal. Physicists call them echoes. Their timing depends on the size and internal structure of the gravastar, making them measurable predictions rather than vague possibilities. If such echoes exist, they could reveal that the object formed after a merger possesses an interior unlike any classical black hole. In the year 2016, one research team reported evidence for these echoes within the first detected merger. The claim sparked intense discussion across the scientific community. Other researchers questioned the statistical strength of the signal, and no broad agreement followed, but the search never stopped. Since then, the Laser Interferometer Gravitational Wave Observatory and the Virgo Observatory have recorded more than 90 gravitational wave events. Every detection has become another opportunity to search for these elusive reflections. None has produced a confirmed result. Current instruments may simply lack the required sensitivity. The proposed Einstein telescope, planned with roughly 10 times the sensitivity of today's detectors, may finally distinguish whether the universe is ringing with black holes alone or with gravastars hiding behind the same gravitational disguise. There are moments when an image changes the way humanity sees the universe. On the 10th of April, during the year 2019, one such moment arrived. After 2 years of processing an immense collection of observations, the Event Horizon Telescope collaboration revealed the first direct image of the shadow cast by a compact object. It marked the first time we had looked upon a feature created by gravity so intense that light itself curved around it. The target rested within the giant galaxy Messier 87, about 55 million light-years from Earth. At its center lies a compact object with a mass estimated at about 6.5 billion times that of our Sunday. Surrounding it was a glowing ring of superheated plasma, the extremely hot electrically charged gas spiraling through powerful gravitational fields. At the center appeared a dark shadow whose size and shape agreed remarkably well with the predictions of general relativity for a black hole. Creating that picture demanded extraordinary cooperation across our planet. 8 radio telescopes, positioned on 4 continents, observed the target simultaneously. Their measurements were synchronized using atomic clocks accurate beyond ordinary comprehension. Vast collections of recorded data were transported on physical storage devices, including shipments flown from the South Pole, where internet connections could not handle the enormous volume. Powerful computational methods then combined these separate observations into a single Earth-sized virtual telescope. The achievement became an international sensation, but another conversation unfolded among theoretical physicists. Could this historic image finally eliminate the gravastar idea? The answer surprised many researchers. It could not. Within months, several peer-reviewed studies demonstrated that the famous shadow alone could not distinguish between a classical black hole and a gravastar possessing the same mass. The dark region appears because gravity bends light into complex paths around an extremely compact object. This effect, called gravitational lensing, changes the direction of passing light through the curvature of space-time itself. Both models produce nearly identical lensing outside their boundaries. But the bright ring surrounding the shadow offers another possibility. Known as the photon ring, it contains subtle information about the geometry close to the object's outer boundary. Tiny differences between black hole and gravastar models may be encoded there. The challenge lies in resolution. The original image simply lacked enough detail to reveal those delicate distinctions with confidence. 3 years later, during the month of April in the year 2022, the Event Horizon Telescope collaboration unveiled another historic image. This time, the target was Sagittarius A star, the compact object at the center of our own Milky Way galaxy, located about 26,000 light-years away and weighing roughly 4 million times the mass of the Sunday. Its appearance proved equally fascinating. Current observations remain compatible with both black hole and gravastar predictions. We now possess extraordinary images of two of the universe's most extreme objects. Yet the deeper question remains unchanged. We have photographed their surroundings with breathtaking precision. We still do not know what truly lies within. Suppose, for a moment, that you could accompany a single particle on its final descent toward one of these extraordinary objects. From a great distance, nothing along the journey would reveal whether the destination was a black hole or a gravastar. Every observation would appear familiar. Every measurement would agree. Both objects curve space-time in almost exactly the same way. Both surround themselves with blazing disks of superheated gas that shine across many wavelengths of light. Both redirect passing light through intense gravitational lensing. Both govern the motions of nearby stars with the same overwhelming pull. Until the final instant, every path through space tells the same story. But everything changes when the boundary is reached. For a classical black hole, there is no physical surface waiting ahead. The event horizon is a mathematical boundary rather than a material one. According to general relativity, an observer crossing it would notice no sudden impact, no flash of heat, and no unmistakable signal announcing the crossing. The journey simply continues inward as space-time carries everything toward the hidden interior. The greatest danger arrives later. Tidal forces, the difference between gravity acting on one part of your body and another, steadily become more extreme. Your feet experience a stronger pull than your head, stretching every atom into an ever longer stream. Physicists call this process spaghettification because matter becomes elongated into thread-like strands. Around a relatively small black hole, this stretching begins before the event horizon is crossed. Around a supermassive black hole, the gravitational gradient at the horizon itself remains surprisingly gentle, allowing an observer to pass through intact before the destructive forces emerge much deeper inside. But a gravastar replaces that gradual fate with an immediate collision. Matter approaching the condensate shell strikes it while moving at an enormous fraction of the speed of light. The encounter resembles nothing like an ordinary landing. It is an impact against one of the densest quantum structures ever proposed by physics. The tremendous kinetic energy carried by the incoming material transforms almost instantly into radiation, spreading back into the surrounding universe. The temperatures produced during this interaction are expected to exceed those found within the Sun's interior, which reaches roughly 15 million degrees Celsius, or about 27 million degrees Fahrenheit. Every atom arriving at the surface is broken apart and converted into radiant energy. Nothing continues into the dark energy region beyond the shell. But gravastar theory leaves room for an even more dramatic possibility. If an exceptionally energetic collision disturbed the delicate balance, maintaining the quantum shell, the confined dark energy could escape in a catastrophic release. Current theoretical models have not yet calculated the full consequences of such an event. The explosion could unfold from the inside outward, driven by forces unlike those expected from any black hole. It remains one of the most extraordinary possibilities suggested by this remarkable alternative picture of gravitational collapse. Far from the bright spiral arms that shape our night sky, countless stars follow paths around an unseen master. Their motions have been recorded for decades, with steadily improving telescopes, revealing a hidden object at the very center of the Milky Way. Among all the places where we might discover whether gravastars truly exist, this may be the most promising. We know this object as Sagittarius A. Its mass equals roughly 4 million suns, compressed into a region comparable to the distance separating the Sun from Mercury. Such an enormous concentration of gravity governs the crowded heart of our galaxy, holding nearby stars in remarkably swift and predictable orbits. One of those stars has become especially important. It is called Star S2, a massive blue star carrying about 15 times the mass of the Sunday. Every 16 years, it completes one full orbit around Sagittarius A. At its closest approach, it races through space at roughly 8,000 kilometers per second, which is about 4,971 miles per second. That speed equals about 2.7% of the speed of light, making it the fastest stellar orbit ever measured directly. But the value of star S2 extends far beyond its astonishing velocity. Since the early 1990s, two research teams, one led by Andrea Ghez at the University of California, Los Angeles, and another led by Reinhard Genzel at the Max Planck Institute, have followed its motion with extraordinary precision. Their decades of observations transformed a distant mystery into a measurable laboratory for gravity, earning them the Nobel Prize in Physics in 2020. Those measurements confirmed something remarkable. The immense mass at the center of our galaxy behaves exactly as general relativity predicts under extremely strong gravity. Every curve of the orbit strengthens confidence in Einstein's theory. Yet the observations reveal only the gravitational field surrounding the object. They do not expose what actually occupies the center. That distinction matters enormously. A black hole and a gravastar with the same mass produce nearly identical gravitational effects at these distances. Star S2 cannot distinguish between them. It traces the surrounding spacetime with extraordinary accuracy, while the true nature of the central object remains concealed. But Sagittarius A offers one unusual advantage. Compared with the brilliant centers of many other galaxies, it consumes surprisingly little surrounding material. Because relatively little gas falls inward, the region is not overwhelmed by an intensely glowing cloud of plasma. That calmer environment gives astronomers a clearer opportunity to search for subtle signatures that could reveal whether a physical surface exists. Several theoretical studies have modeled Sagittarius A as a gravastar and found that its measured mass, its observed shadow, and its faint emissions remain compatible with such a structure. If that possibility proves correct, then the Milky Way has spent billions of years revolving around a vast reservoir of concentrated dark energy. Star S2 would have circled it again and again, while we watched from 26,000 light years away. Every remarkable idea eventually reaches the same demanding test. Can it remain standing once the mathematics is pushed from elegant possibility into relentless examination? For gravastars, that question has never centered on imagination. It has always centered on stability. We have arrived at an object balanced between two extraordinary influences. Gravity pulls relentlessly inward, attempting to compress every part of the structure toward collapse. Inside, dark energy presses outward, creating the opposite tendency across the entire interior. Between them rests an ultra-compressed quantum shell. The entire object exists only if those competing effects remain in perfect equilibrium. But perfect balance can sound fragile. A pencil balanced on its tip falls with the slightest disturbance. A pendulum, however, swings away and naturally returns. Maser and Motola argued that a gravastar behaves more like the pendulum than the pencil. Their original mathematical analysis suggested that small disturbances do not destroy the object. Instead, they produce gentle oscillations before the structure settles back into equilibrium. That prediction invited careful scrutiny from other researchers. Independent teams explored whether the thin quantum shell could survive gradual compression, slow accumulation of surrounding matter, and small external disturbances. They examined how the equations responded when the shell was squeezed, stretched, or slightly displaced from its balanced state. Across many of those studies, the outcome proved encouraging. Minor perturbations generally faded rather than growing uncontrollably, allowing the gravastar to recover its original configuration. But the larger questions remain unsettled. What happens if a neutron star crashes into a gravastar? What if another compact object merges with it, or vast amounts of matter accumulate over time? At those extremes, the mathematics becomes far less certain. Different assumptions produce different futures, and no single description has yet earned broad agreement. Some theoretical models suggest the object can adapt. As additional mass arrives, the shell expands slightly while the dark energy interior grows with it, preserving the overall balance through a form of self-regulation. The gravastar changes size without surrendering its essential structure, remaining stable even as its mass increases. Other calculations point toward a different possibility. They indicate that beyond a critical threshold, equilibrium can no longer be maintained. The shell may lose its stability, allowing gravity to complete the collapse into the very black hole the gravastar was proposed to replace. In that picture, a gravastar represents a metastable state, meaning a condition that can endure for immense spans of time while still possessing an ultimate breaking point. Another challenge remains equally important. The complete formation process has never been calculated in full detail. Mazur and Mottola described the conditions that could halt collapse and outlined the resulting structure. Yet the precise sequence through those final fractions of a second, when ordinary matter reorganizes into a Bose-Einstein condensate under overwhelming gravity, remains incomplete. But this unfinished pathway is the primary reason gravastars have not become the accepted model across astrophysics. The obstacle is incomplete mathematics, not decisive evidence against the idea. One of the strangest ideas ever to emerge from modern physics began with an unexpected conclusion. In 1974, Stephen Hawking showed that black holes are not perfectly dark after all. According to his calculations, they slowly release energy into space, gradually shedding mass over spans of time so vast that they challenge ordinary imagination. The process begins in the quantum vacuum, a state that appears empty but constantly produces fleeting pairs of virtual particles. These pairs normally appear and disappear almost instantly, erasing one another before they can be observed. But conditions change dramatically near the boundary of a black hole. If one particle falls inward while its partner escapes, the pair can no longer reunite. The escaping particle carries away a tiny amount of energy, while the black hole loses an equally tiny amount of mass. Repeated over unimaginable ages, this process slowly causes the black hole to evaporate. But the effect is astonishingly weak. A black hole, formed from the collapse of a massive star, has a Hawking temperature of only about 60 nanokelvins, which means 60 billionths of a degree above absolute zero. By comparison, the cosmic microwave background, the lingering heat left from the beginning of the universe, fills all of space at about 2.7 Kelvin. That background glow is thousands of times warmer than Hawking radiation, completely overwhelming the faint signal we hope to detect. The situation becomes even more extreme for Sagittarius A. Because this object contains roughly 4 million solar masses, its Hawking temperature falls to about 0.00000000000000015 Kelvin. H-teen, one mated demind, was the accestation is the most of the intaxtive Kelvin is the accestations to one mated date, not as mated in accestations, mated in taxestations, mated in taxestations, and that is mated in accestations, mated in taxestations, one mated daughter is, and the accestations is the accestations, is the accestations, mated in taxestations, mated in taxestations, mated in taxestations. That value lies so close to absolute zero that, for every practical observation, it disappears beneath the natural warmth already present throughout the universe. Yet Hawking radiation has never been observed directly. It remains a theoretical prediction produced by combining quantum field theory, which describes the behavior of particles and fields at the smallest scales, with general relativity, which explains gravity as the curvature of spacetime. Physicists regard the result as highly compelling, but direct confirmation still awaits future technology. But gravastars offer a completely different expectation. They possess a genuine physical surface rather than an event horizon. When surrounding matter crashes into that surface, enormous amounts of energy are released immediately as radiation. Instead of producing an almost undetectable whisper above absolute zero, the emission can reach temperatures millions of times greater than Hawking radiation from an object of equal mass. That difference creates an opportunity. The spectrum of radiation, meaning the distribution of light across different energies, should reveal subtle signatures unique to a gravastar when surrounding matter is actively falling inward. At sufficient observational precision, those signatures may separate a gravastar from a black hole that otherwise appears almost identical. The Athena X-ray Observatory, approved by the European Space Agency for launch during the 2030s, has been designed with the sensitivity needed to begin testing exactly that prediction. Every gravitational wave event begins with extraordinary patience. Two compact objects circle one another for millions of years, surrendering tiny amounts of orbital energy as ripples spread across spacetime. Their separation shrinks almost imperceptibly at first, but during the final moments, the pace changes dramatically. The orbit tightens. The motion accelerates to a significant fraction of the speed of light, and the long partnership ends in a collision of almost unimaginable power. When two black holes merge, the event releases more energy within milliseconds than all the stars across the observable universe emit during an entire year. Yet, despite that astonishing violence, the mathematics describing the aftermath remains elegantly simple. The two objects become one. The newly formed black hole vibrates briefly, producing a fading gravitational wave pattern known as the ringdown, meaning the gradual settling of the distorted object into a stable shape. Once those vibrations disappear, no further gravitational signal is expected from the merger itself. But gravastars predict another possibility. A gravastar possesses a physical shell surrounding an interior dominated by dark energy. According to several theoretical models, gravitational waves entering this structure are not completely absorbed. Instead, part of the disturbance reflects from the unusual interior, travels back toward the shell, and escapes into space once again. The merger therefore produces more than one announcement of its existence. The first signal reaches us exactly as expected. Then, after a brief delay measured in fractions of a second pulse could emerge, Another follows after the same interval, then another. Each pulse grows weaker as energy gradually dissipates, creating a repeating pattern called gravitational wave echoes. The delay between echoes depends on the size and internal structure of the merged gravastar, allowing theorists to calculate when each returning signal should appear. This prediction stands apart from nearly every other proposed difference between black holes and gravastars. It is not merely a slight adjustment to an existing waveform, it is an entirely new feature. Classical black holes cannot generate repeated echoes because gravitational waves crossing the event horizon are absorbed rather than reflected. If unmistakable echoes were ever confirmed, they would point toward physics beyond the traditional black hole picture. But detecting those echoes is exceptionally difficult. Their expected strength is far smaller than the primary merger signal, potentially remaining below the sensitivity of the Laser Interferometer Gravitational Wave Observatory for every event recorded so far. The information may already exist within the observations, hidden beneath instrumental noise that current methods cannot fully separate. In 2016, physicists Jahed Abedi, Hannah Dykar, and Nayesh Afshorty reported possible evidence for echoes in the first detected gravitational wave event. Their analysis sparked intense interest, followed by careful re-examination from many independent groups. The debate did not conclude that echoes were impossible. Instead, researchers found that the statistical confidence remained too low for a reliable discovery. But the search continues. Every newly detected merger adds another piece of evidence, another opportunity to uncover a repeating signal that may have been waiting within the data all along. Perspective changes everything. As we climb through the universe's most extraordinary objects, each step reshapes what you thought nature could build. Every level compresses more matter, bends gravity more deeply, and pushes physics closer to its limits. By the time we reach the gravastar, we are no longer comparing ordinary stars. We are comparing the most extreme structures the universe may allow. The journey begins with white dwarfs. These are the exposed cores left behind after stars, much like our sun, exhaust their nuclear fuel. Each is roughly the size of Earth while containing about half the mass of our Sunday. Matter inside is compressed so intensely that a single teaspoon would weigh about 5 tons. They are the most common stellar remnants known, and in about 5 billion years, our own sun is expected to end its life in exactly this form. But gravity can compress matter much further. When a far more massive star collapses, it may produce a neutron star. Although only about 20 kilometers across, that is nearly 12.4 miles, such an object packs roughly 1.4 times the sun's mass into that tiny sphere. Its surface gravity reaches about 200 billion times that of Earth. A teaspoon of neutron star material would weigh roughly 10 million tons. Familiar matter has become something almost unrecognizable. Some neutron stars refuse to remain still. They spin. These rotating remnants are called pulsars, meaning neutron stars that sweep beams of radio waves through space, like enormous cosmic lighthouses. One remarkable example, known as pulsar Juliet 1748-2446 alpha delta, rotates 716 times every second. At its equator, the surface moves at about 24% of the speed of light. The star itself becomes a remarkably precise cosmic clock. But another path leads toward even greater extremes. Magnetars are neutron stars whose magnetic fields surpass almost anything else in nature. Their fields reach about 1 quadrillion Gauss, while Earth's magnetic field measures only about 1/2 Gauss. During December of 2004, a flare from the magnetar known as Sierra Golf Romeo 180 6-20, located about 50,000 light-years away, briefly altered Earth's upper atmosphere. If such a magnetar approached to one-tenth of a light-year, its magnetic field could erase the information stored on every hard drive across our planet. For many years, black holes appeared to mark the final destination. They possess immense gravity, no known physical surface, and a central singularity where our current theories cease to provide meaningful answers. They remain among the deepest mysteries in modern physics. But the gravastar occupies the same territory while telling a different story. Its gravitational pull matches that of a black hole with equal mass. Its influence on surrounding stars appears almost identical. Yet beneath that familiar exterior lies a physical surface, an ultra-dense quantum shell, an interior dominated by dark energy and no singularity at all. It does not stand above black holes in a ladder of greater violence. It stands beside them as another possible ending, equally powerful from the outside, yet perhaps the most structurally intricate stable object that modern physics presently permits. Somewhere beyond the reach of any direct image, we encounter an object whose scale stretches ordinary language almost beyond usefulness. Even after everything we have explored, TON 618 asks us to expand our imagination once again. We are no longer thinking about a compact object inside a nearby galaxy. We are looking across deep cosmic history toward one of the largest known engines in the observable universe. The light arriving at our telescopes today began its journey about 10.4 billion years ago. We see TON 618 as it existed when the universe was only about 3.4 billion years old, less than 1/4 of its present age. It appears as a quasar, meaning an intensely luminous galactic nucleus powered by matter falling toward an extraordinarily massive compact object. Across that immense gulf of time, its brilliance still reaches us. The central object is estimated to contain about 66 billion times the mass of our Sunday numbers. This large become difficult to picture. But if such an object were a gravastar, its diameter would approach about 1,300 astronomical units. That corresponds to nearly 200 billion kilometers, which is about 124 billion miles. By comparison, Pluto circles our Sun at an average distance of roughly 40 astronomical units. This single gravastar would span more than 30 times the width of our outer planetary system. Its interior would be astonishing. Instead of concealing a singularity, the object could contain an enormous region dominated by dark energy, the same mysterious ingredient believed to drive the accelerating expansion of the universe itself. If gravastar theory proves correct, this repulsive interior would occupy a volume larger than most complete planetary systems. The universe may have concentrated one of its most elusive ingredients into a single extraordinary structure, but another spectacle surrounds it. TON 618 launches immense jets of superheated plasma from regions above and below its surrounding disk of infalling matter. These streams race outward at nearly the speed of light and continue for distances comparable to the separation between neighboring stars within the Milky Way. They rank among the largest persistent structures generated by any compact object we have observed. Remarkably, those magnificent jets settle very little. Both conventional black hole models and gravastar models can reproduce them through different physical mechanisms while remaining mathematically consistent with observations. The jets themselves cannot reveal which structure truly occupies the center. They display tremendous power, yet they keep the deeper secret hidden. Distance compounds the challenge, At about 10.4 billion light years away, TON 618 appears far too small on the sky for the Event Horizon Telescope to resolve its boundary. But if this distant giant ultimately proves to be a gravastar, then one of the greatest concentrations of dark energy in the observable universe has existed since the universe was still remarkably young, waiting for us to understand what has been there all along. Few ideas reshape our understanding of reality more completely than the realization that time does not flow at the same pace everywhere. It stretches and compresses according to gravity, turning what feels constant into something remarkably flexible. We experience this effect every day, even though our senses never notice it. You are already living with the proof. Global Positioning System satellites circle Earth at an altitude of about 20,200 kilometers, which is about 12,551 miles, where Earth's gravitational pull is slightly weaker than it is on the ground. Their atomic clocks gain roughly 45 millionths of a second every day compared with clocks on Earth's surface. Unless engineers continually correct that difference, navigation systems would accumulate position errors approaching 10 kilometers, which is about 6.2 miles, every single day. Relativistic time dilation is therefore not an abstract prediction. It is an engineering necessity woven into modern civilization. But gravity has far greater possibilities. As we approach a compact object with several times the sun's mass, time slows by amounts that challenge ordinary intuition. Imagine remaining at a fixed position just outside the boundary surrounding such an object. You might experience only a single second while thousands of years unfolded throughout the distant universe. Entire civilizations could rise and disappear while your own clock barely advanced. The mathematics continues. For a classical black hole, the event horizon marks the point where this slowing appears absolute from the viewpoint of a distant observer. An object falling inward seems to move ever more slowly. Its light becomes increasingly red, meaning every wave is stretched toward lower energy by gravity. Eventually, the object appears frozen near the boundary, fading steadily as its light loses more and more energy. From far away, the final crossing is never actually witnessed, but a gravastar changes only the ending. Outside the object, space-time follows the same geometry predicted for a black hole of equal mass. The curvature is identical, the gravitational pull is identical. Even the pattern of slowing clocks remains identical almost to the boundary itself. Nothing in the surrounding region announces that a different internal structure may exist. The distinction emerges only where the journey ends. Instead of crossing a mathematical boundary from which nothing returns, infalling matter reaches a genuine physical surface formed by the condensate shell. To a distant observer, the approach still appears endlessly delayed because gravity continues stretching time and reddening the escaping light. Yet the story does not end with disappearance. When matter finally collides with that surface, its energy can be transformed and emitted outward once again. That final signal matters. Its timing, spectrum, and structure could preserve clues about the surface that produced it. A black hole conceals every detail beyond its horizon. A gravastar, despite wearing almost the same gravitational disguise, may eventually answer back. In that tiny difference between permanent concealment and delayed return, time itself becomes another way the universe may reveal which kind of object truly waits in the darkness. Some of the strangest ideas in physics have already left the laboratory and entered the world of measurement. Before we can understand the shell surrounding a gravastar, we must briefly step into that proven realm where matter behaves in ways that seem to resist ordinary intuition while remaining completely consistent with experiment. The journey begins with quantum mechanics, the theory describing nature at the smallest scales. Within this framework, an electron does not occupy one definite location before measurement. Instead, it exists in a superposition, meaning many possible locations are described at the same time by a mathematical wave of probabilities. Only when an interaction occurs does one outcome become physically realized. The underlying rules are unfamiliar, yet countless experiments have confirmed them with remarkable precision. But quantum behavior does not always remain microscopic. Under conditions approaching absolute zero, or approximately minus 273 degrees Celsius, or minus 459 degrees Fahrenheit, certain particles known as bosons undergo an extraordinary transformation. Rather than behaving as countless separate particles, they merge into one shared quantum state. Physicists call this a Bose-Einstein condensate. Every participating particle follows the same quantum description, causing the entire collection to behave as one enormous quantum object instead of an assembly of independent pieces. The distinction is profound. In ordinary matter, disturbances spread from particle to particle through countless local interactions. A crystal can fracture, a metal plate can bend. Every region responds according to its own immediate surroundings, but a Bose-Einstein condensate reacts collectively because its components share the same quantum condition. The response belongs to the entire system rather than to isolated fragments acting independently. This collective behavior lies at the heart of the Gravastar proposal. Mazur and Mottola suggested that the thin shell surrounding the dark energy interior exists in this condensate state. Instead of being built from separate particles pushing against one another like atoms in ordinary solids, the shell functions as a unified quantum structure that may possess the mass of an entire collapsed star. Every disturbance would therefore involve the shell as a whole, rather than a chain of local mechanical failures. That possibility changes how stability is understood. A crack propagating through conventional matter depends upon weak points developing one after another. A condensate has no comparable internal arrangement. According to the theory, pressure applied at one location becomes a response distributed throughout the complete quantum state. This collective behavior formed one of the strongest arguments supporting the proposed stability of the gravastar. Laboratory experiments have already revealed surprising consequences of Bose-Einstein condensates. During the year 2000, physicist Lene Howe and her colleagues at Harvard University slowed pulses of light to roughly 17 meters per second, which is about 56 feet per second, while passing them through such a condensate. No classical material had ever displayed anything comparable. A stellar mass condensate surrounding a dark energy interior remains entirely theoretical. Yet every concept used to describe its remarkable quantum behavior already belongs to physics that has been observed, tested, and measured. Ideas can survive for decades, sometimes centuries, without a final answer. Physics eventually asks something more demanding. It asks nature to respond. For the gravastar, that response will come through machines designed with extraordinary precision, each one extending our senses farther than any previous generation imagined possible. The first of these observatories is the Einstein telescope, a proposed third-generation gravitational wave detector planned deep beneath Europe. Engineers are evaluating locations in Sardinia and along the border region shared by the Netherlands, Belgium, and Germany. Built approximately 200 kilometers which is about 124 miles, to 300 kilometers, which is about 186 miles, below the surface would be impossible. So instead, the facility will lie about 200 meters, which is about 656 feet, to 300 meters. That is nearly 984 feet underground, where vibrations from the surface are greatly reduced. Its triangular design will contain arms 10 kilometers long, which is about 6.2 miles, allowing measurements roughly 10 times more sensitive than the current laser interferometer gravitational wave observatory. That improvement matters. Signals predicted from gravastar mergers may be too faint for today's detectors, but the repeated gravitational echoes discussed earlier could emerge above the background noise once this new observatory begins operating during the 2030s. A pattern hidden today may become unmistakable. Another observatory will leave Earth entirely. The Laser Interferometer Space Antenna, approved by the European Space Agency, will consist of 3 spacecraft flying in a vast triangular formation. Each spacecraft will remain separated by approximately 2.5 million kilometers, which is about 1.6 million miles, while following Earth around the Sunday. This enormous detector will measure gravitational waves thousands of times lower in frequency than those detected from the ground. Those longer waves are expected from mergers involving the largest compact objects in the universe, where possible gravastar signatures may appear within the prolonged ringdown, the fading vibration that follows a collision. But gravity is only one messenger. The next generation Event Horizon Telescope proposes adding radio telescopes in space, increasing image sharpness by roughly a factor of 5 compared with the original array. That improvement could reveal fine details within the photon ring surrounding Sagittarius A. Those delicate structures carry information about the geometry immediately surrounding the compact object, offering another opportunity to compare gravastar predictions with observation. The Advanced Telescope for High Energy Astrophysics will contribute from another direction. Also approved by the European Space Agency for launch during the 2030s, it will examine high energy radiation from compact objects with unprecedented spectral precision. If a gravastar possesses a physical surface, the emitted radiation should differ from the signatures expected around an event horizon. Each instrument asks the universe the same question through a different language. One listens to ripples in spacetime, another resolves structure, another studies energetic light. Together, they transform a mathematical possibility into a testable scientific prediction. But once these observatories begin their work, speculation gradually yields to measurement, and nature alone decides the answer. Scientific ideas do not become accepted because they are imaginative. They become accepted because they survive repeated attempts to prove them wrong. That standard has shaped every major discovery in modern astronomy, and it explains why gravastars remain outside the scientific consensus, despite the attention they continue to receive from a small group of researchers. At present, the simpler explanation remains the black hole. Physicists often appeal to the principle of parsimony, commonly called Occam's razor. The idea is straightforward. When two explanations describe the same observations equally well, the one requiring fewer assumptions is generally preferred until new evidence demands greater complexity. General relativity naturally predicts black holes from gravitational collapse. Gravastars require additional ingredients, including a Bose-Einstein condensate forming at stellar densities, a concentrated region of dark energy, and a phase transition, meaning a sudden change in the state of matter, whose detailed physics has yet to be fully calculated. But simplicity alone never decides science. Observations carry greater authority than elegance, and the strongest evidence currently available comes from gravitational wave astronomy. Every compact object merger detected so far has produced waveforms matching the predictions of general relativity with extraordinary precision, remaining comfortably within measurement uncertainties. Those observations strongly support black holes. Yet they do not completely exclude gravastars because two objects sharing the same external gravitational geometry produce virtually identical in spiral signals before the final moments of merger. The greatest technical challenge lies elsewhere. No calculation has yet described, from beginning to end, how a collapsing stellar core could transform into a gravastar. Researchers still seek the complete sequence of events. How rapidly would the condensate form? Under exactly what densities and pressures would the transition begin? How would the shell stabilize before continued collapse overwhelmed it? Until those questions receive predictive mathematical answers, the theory remains incomplete. That incompleteness deserves careful scrutiny. Scientific skepticism is often misunderstood as rejection. In practice, it serves a different purpose. It protects the reliability of scientific knowledge by demanding that every proposal withstand the same demanding standards. Gravastar theory is mathematically consistent and physically motivated, but observational confirmation has not yet arrived. Treating it cautiously reflects discipline rather than reluctance. History offers several reminders. During the year 1934, Walter Bade and Fritz Zwicky proposed neutron stars less than 2 years after the neutron itself had been discovered. Many physicists considered such objects implausibly exotic. More than 3 decades later, during the year 1967, observations finally revealed pulsars, confirming neutron stars were real. Black holes followed a similar path. Even Albert Einstein doubted that nature would ever produce them, until astronomical evidence steadily erased those doubts. But history provides perspective, not prediction. Some bold ideas eventually become established facts. Others disappear when evidence fails to support them. Gravastars now occupy that uncertain middle ground, neither accepted nor discarded, waiting for observations, capable of deciding whether this remarkable possibility belongs among the universe's genuine structures or only among its most fascinating mathematical visions. A single observation can reshape an entire scientific landscape. Most discoveries add another piece to an existing picture, but some discoveries force us to redraw the picture itself. If one compact object were confirmed beyond reasonable doubt to be a gravastar, the consequences would spread through modern physics with remarkable speed. The first changes would be surprisingly modest. The measured masses of compact objects would remain unchanged. The motions of orbiting stars would remain exactly as recorded. Every gravitational wave in spiral detected so far would continue matching observation. But the interiors of these objects would become open questions once again. Every object presently classified as a black hole would immediately become a candidate for careful re-examination, not because previous measurements were incorrect, but because those measurements reveal only what happens outside the boundary. But the deeper consequences would reach much farther. For more than a century, the singularity has represented the point where the mathematics of general relativity ceases to provide physically meaningful answers. If gravastars replaced black holes, that singularity would disappear from every confirmed compact object. Gravity would remain extraordinarily powerful without requiring an infinitely dense point hidden beyond an event horizon. The long search for a theory uniting quantum mechanics with general relativity would continue because the earliest moments of the universe still demand such a framework, yet one of its greatest motivations would become far less immediate. Other long-standing puzzles would also change. The information paradox and the firewall paradox both arise from the existence of an event horizon. Remove that boundary, and those debates take on an entirely different character. The decades of work contributed by Stephen Hawking, Leonard Susskind, Juan Maldacena, Joseph Polchinski, and many other physicists would not lose their value. Instead, those ideas would become part of a different investigation, guiding new questions about quantum surfaces rather than inaccessible interiors. Dark energy would also acquire a new identity. Today it is understood through its influence across the expanding universe, but confirmation of a gravastar would suggest that dark energy can also exist as a concentrated physical component inside an astronomical object. Its nature would remain mysterious, yet researchers could begin studying its behavior through direct observations instead of relying only upon the evolution of the cosmos itself. Every recorded gravitational wave event would deserve another examination. Searches that originally focused on mergers alone would begin looking for the faint repeating echoes predicted by gravastar models. Signals once dismissed as statistical fluctuations could be tested again using improved methods developed after the original detections. But perhaps the greatest shift would be conceptual. For generations, we have pictured the center of our galaxy as the home of the most destructive object it contains. A confirmed gravastar would replace that image with something entirely different. Only about 26,000 light years away, a region of perfect equilibrium could exist, where immense gravity and concentrated dark energy remain balanced inside one enduring quantum structure, while countless stars continue their patient orbits around the heart of the Milky Way. Imagine gathering together everything you have ever touched, every mountain, every ocean, every star visible across the night sky, and every telescope humanity has ever raised toward the cosmos. Together, they represent only a remarkably small fraction of reality. As our journey has unfolded, we have steadily expanded the boundaries of the known, but those boundaries still surround a far greater landscape that remains unexplored. Ordinary matter accounts for only about 5% of the universe's total energy content. Everything familiar belongs within that narrow share. Every atom inside your body, every molecule drifting through a cloud, every planet circling a distant star, and every galaxy whose light has reached our instruments is built from this ordinary material. It is the substance from which every laboratory, spacecraft, and observatory has been constructed, yet it forms only a small island, surrounded by an immense cosmic ocean whose contents remain largely unidentified. But another component reveals itself through gravity alone. During the 1970s, astronomers measuring the rotation of galaxies discovered something deeply unexpected. Stars far from galactic centers traveled much faster than visible matter could explain. Their motions implied the presence of vast quantities of unseen mass. This invisible component became known as dark matter, accounting for roughly 27% of the universe's total energy content. Decades of increasingly sensitive experiments have searched for the particles responsible. None has yet delivered a confirmed direct detection, leaving its true nature unresolved. An even greater mystery emerged later. In 1998, careful observations showed that the expansion of the universe is accelerating instead of slowing. The unknown influence driving that acceleration became known as dark energy. It appears to contribute approximately 68% of the universe's total energy content. Some theories suggest it is a property of empty space itself, sometimes called vacuum energy, the energy predicted to exist even in apparent emptiness because of quantum mechanics. But the value predicted by quantum theory exceeds the observed value by roughly 1, followed by 120 zeros, the largest known disagreement between theoretical prediction and astronomical observation. That perspective changes our sense of certainty. Roughly 95% of everything that exists has never been directly identified. We observe its influence, we measure its effects, yet its underlying nature remains hidden from us despite generations of investigation. But this is where the gravastar idea becomes unusually compelling. If such objects exist, they would occupy the meeting point of two profound mysteries. Their outer shell would represent quantum matter behaving collectively on an astronomical scale, while their interior would contain concentrated dark energy confined within a stable structure. Rather than serving only as extraordinary gravitational engines, the compact objects at galactic centers could become the universe's largest natural laboratories, conducting experiments across billions of years under conditions that no human civilization could ever hope to reproduce. Our understanding has always depended on messages that began their journeys long before anyone existed to receive them. Every beam of light entering a telescope, every passing ripple in space-time, and every faint signal crossing the darkness arrives carrying news from another age. We never witness the universe as it is. We encounter it as it was, assembled from countless moments, spread across unimaginable distances. The observable universe extends to a radius of about 46 billion light years. Within that immense volume lie an estimated 2 trillion galaxies, each following its own history across cosmic time. Nearly every large galaxy appears to possess a compact object at its center, serving as the gravitational anchor around which billions of stars slowly orbit. If gravastars exist, then as many as 2 trillion of these extraordinary objects may already inhabit the observable universe, each potentially surrounding a confined region of dark energy hidden beyond direct inspection. That possibility reshapes the scale of the question. The closest candidate rests at the center of our own galaxy, about 26,000 light years away. The light reaching us today departed that region 26,000 years ago. At that time, anatomically modern humans decorated cave walls in what is now France, while vast regions of the world remained untouched by permanent settlements. Everything we observe from that galactic center belongs to an era separated from us by the entire span of recorded civilization and much more. But the distant universe stretches this separation beyond ordinary imagination. Some of the farthest quasars ever observed shine from more than 13 billion light years away. Their light began traveling when the universe itself was less than 1 billion years old. The compact objects producing those brilliant emissions may have changed completely since then. They may have gathered more matter, merged with companions, or evolved into forms we cannot yet predict. We possess only the ancient record carried by their light. Distance imposes another profound limit. The nearest star beyond our sun lies about 4.2 light years away. A message transmitted today would require 4.2 years to arrive and another 4.2 years before any reply could return. The nearest major galaxy beyond our own stands roughly 2.5 million light years away, placing its central compact object permanently beyond any meaningful exchange across human history. But the universe has never promised immediate answers. Instead, it reveals itself through patient observation. Light becomes testimony. Gravitational waves become evidence. Every photon and every ripple carries information across expanses that reduce every human lifetime, every civilization, and every scientific generation to a brief instant. We ask our questions only once, yet the universe has already begun answering them, sending its replies across distances so immense that discovery depends less upon speed than upon our willingness to keep listening. There is a particular kind of mystery that feels closer than the rest. It does not belong to the edge of the observable universe or to galaxies whose light began traveling before Earth existed. It resides within our own galactic home, at the hidden point around which every spiral arm, every wandering cloud, and every familiar star has been arranged for billions of years. We know that center exists. You can calculate its influence with extraordinary confidence, yet its true nature remains concealed. The star known as Saint 2 circles Sagittarius A with remarkable precision. Its complete journey around the galactic center requires about 16 years, allowing astronomers to watch nearly an entire orbit within a single scientific career. Careful measurements have revealed the mass of the central object to within only a few percent of uncertainty. Those observations have also detected orbital precession, the gradual rotation of an orbit through space predicted by general relativity. The same phenomenon appears in the orbit of Mercury around the Sun. Although around Sagittarius A, the effect is dramatically stronger because the surrounding gravity is vastly more intense. Every new observation sharpens the picture. We know how rapidly nearby stars travel. We know how their paths bend through curved spacetime. We know how much mass must occupy the galactic center to guide those motions. We can even watch matter whirl inward while releasing tremendous energy before disappearing from view. Yet all of those discoveries describe only the exterior behavior of the central object. None reveals what lies beyond its boundary. But that distinction changes everything. Imagine understanding every planet in the solar system with exquisite accuracy while remaining unable to determine whether the sun itself was truly a star. Every orbit would still make sense. Every calculation would remain correct. Yet the central question would remain unanswered. That is the position modern astrophysics occupies when confronting compact objects. Their outward influence has been measured with astonishing precision, while their internal structure continues to resist direct observation. This form of ignorance is remarkably precise. Humanity has developed instruments capable of detecting distortions in spacetime smaller than the diameter of a proton produced by events more than 1 billion light years away. We have reconstructed the shadows surrounding a compact object 55 million light years from Earth. We have followed a single star racing around the Milky Way's center at roughly 8,000 kilometers per second, which is about 4,971 miles per second. Each achievement has expanded the frontier of measurement. But one question continues to endure. What exists beyond the boundary we cannot cross? A singularity, a gravastar, or something still unimagined would produce the same graceful dance of nearby stars until evidence finally separates one possibility from another. The universe has revealed almost everything surrounding the center. It has simply withheld the answer, waiting at the center itself. Some mysteries measure time differently than we do. They outlive generations, careers, and entire schools of thought, remaining unchanged while the people who pursue them gradually hand their work to those who follow. When we look at the deepest questions in physics, we are also looking at histories that unfold across lifetimes rather than moments. In 1916, Carl Schwarzschild discovered the mathematical solution that eventually led physicists toward the idea of a singularity. More than 100 years have passed since that breakthrough, yet the singularity itself remains unresolved. Equations continue to describe its consequences with extraordinary precision, while the true nature of its interior still escapes complete understanding. The mathematics points toward an answer that physics has not yet fully explained. Another puzzle joined that list decades later. In 1976, Stephen Hawking formally described the black hole information paradox, exposing a profound tension between quantum mechanics and general relativity. Nearly half a century has passed without a universally accepted resolution. Then, in 1998, astronomers established that dark energy dominates the expansion of the universe. More than 2 decades later, its fundamental character remains one of the greatest unanswered questions in science. Gravastar theory entered this landscape in 2001, offering another possible path through these difficulties. After more than 2 decades of study, it has been neither confirmed nor ruled out. But none of these unanswered questions represents failure. They have attracted some of the most accomplished mathematical minds in history. Stephen Hawking, Roger Penrose, Edward Witten, Juan Maldacena, Leonard Susskind, and thousands of other researchers have devoted immense effort to understanding the same fundamental problems. Their work has continually refined the questions, even when definitive answers remained beyond reach. The boundary has persisted because present mathematics and present instruments still leave parts of reality inaccessible. History offers a reassuring pattern. Ideas that once seemed permanently speculative have repeatedly crossed into observation after years of patient preparation. The cosmic microwave background was predicted in 1948 and discovered unexpectedly in 1965. Gravitational waves were predicted in 1916 before finally being detected in 2015. The Higgs boson was proposed in 1964 and confirmed only in 2012 after generations of experimental development. But those intervals reveal something important. The distance between prediction and confirmation in physics is commonly measured in decades. Sometimes it extends across half a century or longer. Compared with that history, the questions surrounding gravastars, dark energy, and compact objects are still remarkably young. We often experience them as ancient because they have accompanied much of our own lives, yet by the slower rhythm of scientific discovery, they may simply be waiting for the observation, the instrument, or the insight that allows the universe to reveal what has been present all along. It is easy to measure science by the questions it has not answered. Yet the greater perspective comes from remembering how much of reality was once completely hidden from human understanding. The landscape we now consider familiar was, only a short time ago, beyond imagination, waiting for observations that had not yet been made and instruments that had not yet been built. At the beginning of the 20th century, atoms were still imperfectly understood, and the structure we now assign to them had not yet emerged. Quantum mechanics did not exist. General relativity had not been written. Nuclear physics remained undiscovered. No one knew the universe was expanding. The cosmic microwave background had not been detected. Dark matter and dark energy had not entered scientific language. Neutron stars, black holes, and gravitational waves belonged only to the future. But discovery accelerated. Across little more than a century, physics advanced from identifying the electron to recording ripples in spacetime itself. Humanity eventually produced an image of the shadow surrounding a compact object containing about 6.5 billion times the mass of our Sun, located roughly 55 million light-years away. Instruments also measured a space-time disturbance smaller than a proton, created by a merger approximately 1,300,000,000 light-years from Earth. Achievements that would once have resembled fantasy gradually became ordinary scientific results. This pace has no historical parallel. Each generation inherited questions that seemed impossible, then transformed them into measurements. Every successful instrument widened the horizon a little farther. Every new observation revealed another layer of complexity, while confirming that nature consistently rewards careful patience over quick certainty. But that pattern continues today. The observatories expected to examine gravastar theory belong naturally within this long progression. The Einstein telescope is planned. The Laser Interferometer Space Antenna has received approval. Future expansions of the Event Horizon Telescope continue to be studied. These are practical extensions of existing technology rather than distant dreams. Their purpose is straightforward: to observe the universe with greater precision than any previous generation could achieve. Meanwhile, the universe has never stopped providing the evidence. Gravitational waves from merging compact objects continue crossing Earth every moment. Some carry the fading vibrations known as ring-down signals, the final oscillations that follow a merger before the newly formed object settles into equilibrium. If gravastars exist, subtle echoes may already be hidden within those waves, waiting for detectors capable of separating them from surrounding noise. The information has traveled across space for millions or billions of years. Only our ability to receive it remains incomplete. What we already know would have astonished nearly every civilization that came before us. We have learned that space-time bends, that the universe expands at an increasing rate, that quantum states can shape the behavior of entire materials, and that gravity itself can send waves across the cosmos. But history suggests an enduring lesson. Every profound answer has expanded the boundary of mystery rather than reducing it, making the next discovery seem even more extraordinary than the last. Some scientific questions remain confined to laboratories or equations. Others stretch across the architecture of the cosmos itself. The gravastar question belongs to the second kind. It asks what occupies the most extreme gravitational environments known, objects distributed throughout nearly every large galaxy, influencing systems so vast that their effects extend across billions of stars and countless generations of cosmic history. Wherever we look, the pattern repeats. Large galaxies appear to gather around immensely compact central objects whose gravity shapes stellar motions, guides enormous clouds of gas, and influences when new stars emerge. Over billions of years, these central engines help determine the appearance of entire galaxies, affecting the environments where planets eventually assemble and where, under favorable circumstances, life may arise. The consequences reach much farther than the immediate neighborhood surrounding the central mass. But imagine the implications if those compact objects are gravastars. The great anchors of galaxies would no longer represent regions where known physics collapses into unresolved singularities. Instead, they would become stable quantum structures, maintaining an extraordinary balance between immense gravity and concentrated dark energy. The centers of galaxies would resemble natural laboratories where the deepest laws of nature achieve equilibrium under conditions impossible to reproduce anywhere else. That possibility changes the story. The objects long regarded as the universe's most fearsome destinations would also become examples of remarkable stability. Their outer regions would remain unimaginably dangerous, where gravity dominates every nearby path and escape becomes impossible through ordinary means. Yet beneath that extreme exterior, The mathematics proposes a carefully maintained interior configuration rather than limitless collapse. Destructive surroundings would enclose persistent order. The contrast is striking. Violence at the boundary, balance within. Immense gravitational pressure surrounding a quantum state that responds collectively rather than fragmenting under local disturbances. If this picture proves correct, then nature accomplishes something profoundly elegant at the very edge of physical possibility, replacing catastrophic collapse with enduring equilibrium. But none of this requires mysticism. It follows directly from mathematical models that remain under investigation, models demanding observational evidence before they can move beyond hypothesis. Physics has repeatedly revealed realities that seem stranger than expectation while remaining entirely governed by consistent natural laws. Quantum mechanics, space-time curvature, gravitational waves, and cosmic expansion all appeared astonishing before observation established them as features of the universe itself. Perhaps that is the deeper lesson accompanying this search. When we ask what lies at the center of the Milky Way, we are also asking what kind of universe we inhabit. We are asking how dark energy truly behaves, whether information survives the most extreme conditions, and whether the laws of physics remain internally consistent across every observable scale. The answer, whatever it becomes, will describe far more than one distant object. It will describe the character of the universe that has surrounded us from the beginning. Every field of science eventually reaches a frontier where observation slows and inference begins. At that frontier, the limitation is not imagination or determination. It is the architecture of reality itself. Some answers may exist in full detail while remaining forever separated from direct inspection by the physical rules governing the universe. Consider the interior of a genuine black hole. If the conventional picture is correct, every path beyond the event horizon leads inward, and no signal can ever travel back across that boundary. Light cannot escape. Matter cannot escape. Information cannot return in any form accessible to an outside observer. Whatever happens near the singularity, if such a region truly exists, remains permanently beyond direct measurement by any instrument that could continue sending observations outward. But the Gravastar proposal arrives at the same destination through a remarkably different route. Its interior is also hidden, although the reason changes completely. Matter approaching the surface never reaches the dark energy core itself. Instead, it encounters a physical quantum boundary that absorbs, responds, and re-emits energy according to its own properties. The concealed interior remains isolated because entry never occurs. The barrier is not a one-way horizon. It is a material surface preventing direct access from the beginning. The outcome appears surprisingly similar. Whether the universe contains black holes or gravastars, the deepest interior remains concealed from straightforward observation. From our distant perspective, each object withholds its central structure, offering only the behavior of its exterior for careful study. We learn by examining consequences rather than witnessing the hidden processes themselves. But science has encountered this pattern before. The internal structure of the proton remained mysterious until particle accelerators reached energies capable of revealing its constituent particles. The molecular arrangement of deoxyribonucleic acid resisted understanding until the development of powerful methods using X-rays to reveal atomic organization. Even the cosmic microwave background, the oldest observable light in existence, remained beyond human knowledge until radio telescopes achieved sufficient sensitivity to detect its faint glow across the sky. Each advance shifted the boundary. Knowledge expanded, Because mathematics improved, instruments became more capable, and many independent observations gradually converged toward the same explanation. Direct viewing was rarely the first step. Indirect evidence accumulated until alternative interpretations became increasingly difficult to defend. The search for gravastars follows that same tradition. If future observatories detect gravitational wave echoes, those repeating signals would not reveal the hidden interior like an ordinary photograph. Instead, they would resemble a carefully measured response from an otherwise inaccessible boundary. The returning pattern produced when gravitational waves interact with a physical surface surrounding concentrated dark energy. We would still remain outside. Yet the returning signal could reveal the character of what lies beyond, reminding us that science has often learned its deepest truths by listening carefully to what the universe chooses to send back. When you stand beneath a truly dark sky, far from the glow of cities, your eyes gather only a tiny fraction of what surrounds you. Under excellent conditions, you can see roughly 5,000 stars across the entire sky, every one belonging to the Milky Way, and almost all lying within only a few thousand light years of Earth. Even that familiar view is only the nearest layer of a far greater reality. Beyond those visible stars stretches an unseen population of approximately 200 billion to 400 billion more stars within our own galaxy. Beyond the Milky Way lie about 2 trillion additional galaxies, each containing billions of stars arranged into unique histories across cosmic time. At the center of nearly every large galaxy rests a compact object whose true nature remains one of modern astronomy's deepest unanswered questions. But the sky is also a record of time. The light arriving from the nearest star has traveled for about 4.2 years before reaching your eyes. Light from the Andromeda Galaxy began its journey roughly 2,500,000 years ago. The most distant known quasars send us light that has crossed approximately 13 billion years of expanding space, revealing the universe as it existed when it was still remarkably young. Every direction becomes a different chapter in a history written across immense distances. Most of that story remains invisible. Human vision detects only a narrow band of light. The universe also speaks through infrared radiation, radio waves, X-rays, gamma rays, and gravitational waves, each carrying information unavailable to ordinary sight. Hidden within those signals are the emissions produced near the boundaries of compact objects. Some may contain subtle signatures capable of distinguishing gravastars from black holes. Present instruments have approached that threshold, yet they have not fully crossed it. The sky, therefore, becomes something unexpected. It is not merely scenery above us. It is an archive whose pages are written in wavelength, timing, polarization, and gravity. Every observation adds another translated sentence, while countless others remain beyond our present ability to interpret. The document itself is already complete. Our reading of it continues to evolve. But history encourages patience. Each generation has inherited a richer understanding of the heavens than the one before it. Constellations became stars. Stars became galaxies. Galaxies became an expanding universe filled with phenomena once considered impossible. There is little reason to believe that our own generation has reached the final chapter of that unfolding story. The compact objects at galactic centers have existed for billions of years, shaping their surroundings without concern for whether anyone observes them. They will continue their work for billions more. They ask for no attention and offer no explanations. They simply persist, sending their messages across the cosmos, waiting for instruments and minds capable of understanding what has always been there. Science has always moved through uncertainty with remarkable discipline. It does not promise permanent certainty, nor does it defend old ideas simply because they are familiar. Instead, it offers the strongest description that current evidence can support, then changes course whenever better evidence appears. You and we inherit that tradition each time we look toward the sky. Today, the strongest description of these compact objects remains the black hole. General relativity predicts their existence with extraordinary precision, and every observation made so far fits comfortably within that framework. The motions of stars, the bending of light, the images of enormous compact objects, and the gravitational waves recorded from distant mergers all agree with those predictions. That agreement deserves confidence because it has survived every serious observational test. But another possibility remains. The gravastar is mathematically consistent, physically motivated, and has not been excluded by any existing observation. For more than 23 years, it has remained within the peer-reviewed scientific literature, offering a different interior while preserving almost every measurable feature visible from the outside. If future observations support that description, several of the deepest puzzles in modern physics could take on entirely different meanings without overturning everything already learned. Both statements can exist together. The universe has not yet forced a final choice. Only observation can do that, and observation unfolds at its own pace. The center of the Milky Way lies about 26,000 light years away. Whatever is happening there at this moment will not be seen from Earth for another 26,000 years. If two compact objects were merging there today, the gravitational waves from that event would also require 26,000 years before reaching detectors built by humanity. Every listener sharing this moment will be part of history long before those signals arrive. But older messages continue their journey. Some mergers occurred thousands, millions, or even billions of years ago, and their signals are reaching Earth now. Others have already passed through our planet, preserved within archived observations collected across the world. Researchers continue examining those records with steadily improving methods, searching for patterns that earlier analyses could not yet recognize. Every refinement expands what existing data may still reveal. The universe has conducted this experiment for approximately 13,800,000,000 years. Humanity has possessed the tools to ask these questions for only about 100 years. Instruments designed to probe them more deeply are expected within roughly the next 20 years. Against the age of the cosmos, that remaining wait is astonishingly brief. So we leave the story where science itself leaves it, between confidence and curiosity. The sky continues, speaking across immense distances. The evidence continues arriving. The answers are already traveling toward us, one wave and one photon at a time. Sleep now. The signals are still coming.